Okay, we're going to start this again, part 2, hopefully getting this working. There we go. Hopefully you're able to see a little bit. I'm actually going to go back real quick and just go over this real fast because we basically did it already. But solutions, remember, are very small particles. They're the smallest. And then these are medium. They will catch light. That's known as a Tyndall effect. And then suspensions are the biggest. All right, so as we look at this, if we just took different colors, and I highlighted them on the other thing, but I'm going to do them really quickly again. So solutions would be the smallest particles. So these are ones that we can't really see. Here we got gas, saline. I think that's all I did on that one. If we did colloids, colloids can be a little bit bigger. They can catch light, but they don't fall out. That's the key. They're bigger particles, but they don't fall out of solution. So here we've got tomato soup would probably be. A dental filling is a solid emulsion. It's a type of colloid. Tap water, you put light through, you'd be able to see something. Fog, jello, mayonnaise, and that's about it. Okay, the others, what's left, will fall out of solutions, and so we get suspensions, and that would be the chocolate chips will actually fall out of milk and chocolate chip if you heat it up just a little bit. Octane, muddy water, chocolate milk. Anytime you end an ANE or ONE and water, it's going to not mix. Sodium bromide and carbon tet. Sodium bromide is ionic, carbon tet is covalent because they're close together. Nonane and water, again, covalent ionic. Clam chowder, the clams will fall to the bottom. Vegetable beef, the vegetables and beef will fall to the bottom. So that's really quickly that one. I'm just sort of reviewing these really quickly. I've already got them on another video, but I don't know that the sound was working either. So on this one, we're wanting to find out what would dissolve in water. So remember, when we're dissolving something in water, we want to remember NOF, nitrogen, oxygen, fluorine directly connected to a hydrogen, and we want to remember NAG-SAG. And on NAG-SAG, NAG is always soluble. The A's are always soluble. NAG is nitrate, NO3 minus. A is acetate, CH3CO2 minus. And G is group 1 metals. Group 1 metals would be like sodium, potassium, that column. And this A is ammonia, which is NH4 positive. S is sulfate, SO4 2 minus, sulfate. Let's write the AL. Sulfate, and then G here is group 17, which is fluorine, chlorine, bromine, that column. Okay, now two of them, the SAG and the G and the S, they have exceptions. The first exception is PMS. That means when they mix with lead, mercury, or silver, they're not soluble. The other one is only problem with the sulfate. I'll put that right here, and that is castrober. And that's representative of calcium, strontium, and barium. And they're not soluble with sulfates. Okay, so having that background really quickly, we're determining what's soluble in water. So anytime we end up with a carbon compound like this, it's not going to dissolve in water. This is not going to dissolve in water. Na is group 1 metal. That is right here. That's going to be soluble. K3PO4, that is also group 1 metal, so it is soluble. PbSO4 falls under sulfates, but we got 2 exceptions here, one of which is lead, so that is not soluble. Methanol falls under the O in not in hydrogen bonding, so it is soluble. And then mercury chloride again falls under group 17 metals, and it's on the M on the PMS, so it is not soluble. Now, looking at the electrolytes, we're going to look also at NAGSAG. So NAGSAG is important here, but not NOF. So when we look at NOF, it is not an electrolyte. Cross through it. Okay, so we're looking at things that are electrolytes here. So group 1 metal, yes. Group 1 metal, yes. Ammonium and sulfate, yes. Group 1 metal, group 17 metal. Oops, here we go with a covalent bond, not part of NAGSAG. Hydrogen, oxygen. It looks like it might be hydrogen bonding, and if you chose it to be hydrogen bonding, that's great, but that doesn't make it an electrolyte. And SO2, again, close together on the periodic table, not covalent, or it's covalent, not ionic. And then when we look at these right here, we also talked about this above. Solutions are the smallest, then colloids, and then suspensions. And then we're going to finish the phrase here. Like dissolves like is the phrase here. That means that polar compounds will be soluble in polar solvents, and nonpolar, if you think about that polar bear we talked about, dissolving in water, and the nonpolar bear not. Okay, again, this is with the solubility rules, this is NAGSAG, and this is also NOF. So when you're looking at solubility, you're looking at these things, and it wants it not soluble. So be careful if she puts not there, you're looking for ones that are not soluble. So really quickly going through this, calcium, nitrate. Nitrates are soluble. Sodium and chlorine are both soluble, group 1 and group 17 metals. Nitrates are soluble. Ammonia and sulfates are soluble. Barium with sulfate is not soluble. That's one of our exceptions, or PMSs. Lead with chlorine is not soluble. That's one of our exceptions. Iron hydroxide is not one of our rules at all, so we count it as not being soluble. This is calcium acetate. Acetate is soluble. Silver chloride. Silver is one of the PMS. It's not soluble. All right, on this next part right here, I'm just catching you up real fast. These are the choices that you can put to increase or decrease solubility. So as we're looking here, solubility of solid KCl in water, that's like dissolving salt in water. What would increase it? As we look over here, with things that would increase it, the pressure would have no effect. Decreasing the temperature would actually decrease the solubility, so we would put C over here. Increasing the temperature would increase the solubility. Stirring the solution would increase the solubility, and crushing whatever the solid was before I put in the solution would increase the solubility. Now, what would increase the solubility in water? Now, she might get a little tricky with those last two, the stirring and the crushing. They don't really increase the solubility, they help it to dissolve faster. So I'm going to just change that. It doesn't really change the solubility, but increasing the temperature definitely does. And decreasing temperature definitely decreases that. So I'm going to say, looking at her test, don't count those two in. That just helps dissolve faster. It doesn't increase the solubility. And I'm working with sun here. You can see it on my paper. I'm trying to stay out of it so I can keep going for you. Okay, the solubility of gas does have to deal with pressure. So think of pop here when you're trying to remember this. Think of pop. If you have pressure on your pop, then it keeps the bubbles in your pop. So increasing the pressure would increase the solubility of the gas, where decreasing the pressure would decrease the solubility. Now, if you have hot pop, it's not as bubbly as if you have cold pop. It doesn't have as much carbonation in it. So decreasing the temperature of the solution would increase the solubility, whereas increasing temperature would decrease the solubility. Now with gases, stirring does matter. If you stir it, then your bubbles are going to come out of solution, so it's actually going to decrease. Crushing has no effect because it's gas. On the bottom here, we have a solution made by this much of this. We take, and she gives you how to do this. You're going to go weight divided by volume times it by 100%, right? So 7.68 grams divided by 167.8 milliliters times by 100 will give you percent in weight per volume. So plugging it into my calculator here, I want to times it. Got it right first time. 4.58%. Okay, and that would be your answer. So go square your answer, right? Okay, let's go to the next page. I like pages to do, so we're going to move fast. All right, so the solution is made by mixing this much and this much. What is the concentration of ethanol in units of volume per volume percent? So I need the total volume of the solution, so I'm going to need to add these up. So I'm going to take the 38 milliliters of ethanol and I'm going to put it on the top, but on the bottom I'm going to do 269 plus 38 milliliters, and then I'm going to times it by 100 to equal, because this is volume of solution and this is volume of solute. Okay, so when we do this, we're going to take 38 divided by parentheses 269 plus 38, close parentheses. I'm doing this right here, and I get an answer times by 100, and I get 12 point, and there's only really two significant figures, so 12% volume to volume, and that would be my answer. Okay, next one. Here we're looking at weight per volume. So on this one we don't need a total volume on the bottom. So here it gives me this, and it gives me this. So where it's weight per volume, I'm going to put my 5.7 grams on the top, divided by, it's wanting me to know how much, what the volume is. So here's my x, and I'm going to times it by 100, and I'm going to get this number over here, the 0.72%. So solving for x, basically these two just trade places, and I get 5.7 times 100 divided by 0.72 equals x. So plugging in, 5.7 times 100 equals divided by 0.72, and we get 791.92 milliliters. Whenever we do weight per volume, it's grams per milliliter. Okay, next one up. Here we have this many grams of solution and this many kilograms. Be careful here. Kilograms versus grams. They've got to be in the same unit. Okay, so we're going to convert one or the other. Let's go ahead and do this. So I'm going to take the, since it wants parts per million, I'm going to set it up like a test, but I've got to get them in the same unit. So 11.3 grams divided by 1,000 grams per kilogram. So the grams will cancel and the kilograms will come up top. Then I'm going to take and divide that by the 5,100 kilograms, times it by 10 to the 6, because that's a million, and I'll get my answer. And you could do this in 2 steps, that's fine. So 11, let's clear this. 11.3 divided by 1,000. I just like to keep it all in my calculator. So there's that first answer. And then I'm going to take that first answer and divide it by 5100, get an answer. And then I'm going to times it by 10 to the power 6 and hit enter. And I've got 2.21 parts per million. All right, next one. What is the molarity? Remember, molarity is the capital M with mole on top and the lake on the bottom, because the lake gets down in here. So we have got, what is the molarity? So we're trying to find big M. And we've been given moles, and we've been given liters, and we just plug in 5.09 moles divided by 7.50 liters. 5.09 divided by 7.5, and we end up with 0.679 capital M of KCl. Done. Next one. Here we're given grams of NaCl and milliliters of solution, and we're trying to find molarity. So we've got to get them in the right units first, and the right units are, remember, moles over liters. So we're going to have to take this 14.88 grams NaCl, and we're going to need to change it into moles. We're going to need to take this 423 milliliters and change it into liters. That one's an easy one because we've got it already, so it's 0.423 liters. So we can put over here on the bottom 0.423 liters. But we need to add up the mass of NaCl. So Na is 22.99 from the periodic table. Chlorine is 35.45. Add it together, 58.44. Put that on the bottom. That's how many grams are equal 1 mole. Plug that through, 14.88 divided by 58.44. And we get 0.255 moles of NaCl. Put that over here, 0.255 moles, and divide it by the 0.423, and we get 0.602, and that would be capital M NaCl. Okay, next one down here in the bottom. What is the maximum volume? So I'm looking for volume if I have this concentration and that many grams. So again, I'm using that same moles per liter, but this time I'm looking for volume. So I'm going to rearrange the equation, and volume is going to equal molarity times moles. Well, I have grams. So the first step is taking that 185.3 grams of barium chloride and changing it into moles barium chloride. And to do that, I need to add up barium and chlorine. Chlorine I've got memorized, barium I do not. So let's look at barium. And barium is 137.33. And I chose to make this barium instead of calcium because they were off on both of them. If you chose to do calcium, it's going to be 40 point something. Okay? So I'm going to change that, and I'm going to add it up, 137.33 plus 2 times 35.45, and I got 208.23 grams, 208.23 grams barium chloride. Now again, if you did it with calcium chloride, I just changed one and forgot to change the other one. Okay, I'm going to put that on the bottom, and I'm going to times it by 185.3, whoops, 0.3, and I get 0.890 moles of barium chloride. All right, now I've got moles and I've got molarity, so now I'm going to times them together. So molarity 0.588 molar times 0.890 mole will give me 0.516 liters. Done. All right, moving on. I'm going to change colors for a minute because I'm getting tired of that color. Circle which of the ones are not very soluble in water. Again, we're looking at NOF and we're looking at NAGSAG. Let's get this so you can read it. So we're looking at both of these two things, and that did not look very good. So let's try this over again. NOF and nag, sag. All right, so not very soluble in water. Be careful. This is a not. So if it has NOF or nag, sag, then it's going to be soluble in water. So OH, NOF. OH, NOF. Nothing. Oh, there's one that will be not very soluble in water. NOF, not very soluble in water. NOF. This one is not a NOF. That one's not very soluble in water. Remember, it has to have an oxygen directly connected to an H. This has an N directly connected to an H and an O. So that is soluble. Coming over here, no N or O, no nag, sag, so not very soluble in water. OH, OH, no OH. No, yep, OH right here. This one doesn't have an OH, so this one has an OH and an NH, so that is. This one does not have anything, so it's not. This one has a nitrogen to a hydrogen, so that one is soluble. This one is soluble. This one is soluble. So that's what you should have picked for not very soluble. All right, next one. We're looking at what is the concentration of solution formed by adding this many milliliters of water to this many milliliters of water that was at this concentration. This is C1V1 equals C2V2. The concentration times the volume equals concentration times the volume. Specifically, molarity times volume equals molarity times volume. But remember this equation more because it goes with percent, it goes with parts per million, it goes with many other things. So we are solving for C1. We don't have C1. We have V1, we have V2, and we have C2. So plugging in, we just go C1 is equal to C2 V2 divided by V1. Plugging in. 7.2 molar times 205.0 milliliters divided by 165.0 milliliters. Now we're diluting, so it should become less concentrated. Let's see if it does. 7.2 times 205 equals, divided by 165, something's off. Oh, what is the solution? This is the original solution, the first concentration before I diluted. Yes, it'll be more concentrated. 8.95 molar. That is more concentrated, and it would have been of NaCl. All right, next one. Concentration added by diluting this much of this to this. Now I'm looking for the final concentration here. So I'm looking for C2 here. So what is the final concentration by diluting volume 1, concentration 1, sorry, let's just put that down there, and volume 2. So here I'm looking for C2, summing of C1V1 divided by V2, plugging in C1, C1 is 4.3 molar, volume 1 is 36.9 milliliters, divided by V2, 240.0 milliliters, cross out, and we've got 4.3 times 36.9 equals, divided by 240, and we've got 0.66 for the molarity, which is less, which it should be, of KCl. Okay, now we're down to this part. This is the part you need to think about. This is a thinking thing. If all of these are the same, then you're worried about something else. These are all the same. So now you're worried about the I. Remember, the I is how many parts, number of parts it will break into. So this one will break into 3 K plus parts plus 1 PO4 part, giving an I of 4. Sucrose, I of 1. It's covalent. Magnesium nitrate, magnesium plus 2 NO3 minuses, so the I is 3. And then all solution have the same, NaCl, Na plus, Cl minus, I is 2. So I'm looking for the highest boiling point. I want the greatest, I to be the biggest. So the I is biggest in A. All right, on this one, you've got to look at two things. You've got the moles that are changing, and you've got the kilograms that are changing, but the compound is not. So you're not worried about I here. You're worried about molality. Remember, molality is moles divided by kilograms. So just quickly put these in real fast into your calculator. 0.75 divided by 4 gives me 0.1875. 0.77 divided by 1, C is 0.75. I've got my 0 in front of that. 0.25 divided by 0.5 is 0.5. And 0.25 divided by 1 is 0.25. So I'm looking for the one that's biggest. It would be B. All right? Okay, hypotonic. Hypo means, look at hypo. Hypo means lower than. Okay, so hypotonic solution has blank osmotic pressure than as body fluids. So it has a lower osmotic pressure because it's got less. A hyper, think hup, hyper has higher. Okay, go to the next one. Okay, in a hypertonic solution, this was our lab. Hypertonic solution, that's out here more concentrated than in the cell. The cell, that's supposed to be the cells, shrink in a process called, remember it gets little spikies when it shrinks, and it's called crenation. Okay, isotonic solution. Iso meaning same, has blank pressure, the same. Red blood cells are placed in a solution and the cells begin to swell. That means I'm trying to get in there because it's really concentrated inside, and because it swells, it's called hemolysis. How should the solution be classified? It should be hypotonic because the solution is less dilute than inside. Okay. All right. 12A, flask contains two compartments, A and B, with equal volumes separated by a semi-permeable envelope. Draw a diagram that represents the final volume if A was originally 10% weight by volume glucose, and this was 20% weight to volume glucose. So this side was more concentrated than this side, so what's going to happen is this side is going to be higher because it's going to diffuse through. Now this right here was supposed to come with a graph, and this diagram was supposed to be up above. Remember, in the graphs, if you have a line, below is unsaturated and above is supersaturated, and on the line is just saturated. So be able to read it, basically. Okay. You'd be given a solution concentration and have to figure out where it was on the graph. All right. A solution that has more than the maximum is supersaturated. One that has less than the maximum is unsaturated. And one that has the maximum is saturated. Okay, next. What is the interaction that holds for this? So you've got to think about it. So Na plus, I want to keep it in solution. So we talked about this a little bit. So Na plus is here, and then I have these water molecules. The negative part of the oxygen is attracted to the sodium. And because that negative part is attracted to sodium, we still get positives out here because of these hydrogen molecules. Okay? So now I'm thinking about it. Now I'm trying to think, okay, what's going on here? What's keeping this sodium in solution? So is it the ion-ion attraction between Na ions and hydrogen ions? No, hydrogens are positive, and positive repel, so that can't be right. The hydrogen bonding, well, hydrogen bonding is NOF. I don't have any NOF here, that can't be right. Ion dipole interactions between Na ions and oxygen, yes, that's what's happening, that's what's going on. I think that's it, but let's look at the last one. The ion-ion attractions between sodium and chlorine. Well, that's a true statement. There is ion-ion attractions, but it's asking you what's responsible for holding the dissolved ions in the aqueous solution. If these two get together, they form NaCl and they drop out of solution, making a solid. Okay, so how can the solubility of a substance be described? You can describe it as saturated, supersaturated. I'm not going to write it all. Super saturated or unsaturated. Okay, and it is usually described in grams per milliliter. All right, next page. The following statements are true or false, so let's look at this. The number of moles of solid present in exactly 1 liter of solution is referred to as the solution's molarity. The moles of solid present in exactly 1 liter solution. Well, molarity is moles per liter. Well, this one is a little bit tricky. Excuse me. Because the bottom, when you're finally done and you get 1.8 molar, then that would be how many moles per liter, which is true. But you can put different amounts of moles here and different amount of liters here to get that final answer. It doesn't have to be exactly 1 liter down here. So I'm focusing in on this exactly 1 liter, and so I would probably say false. I'll have to look at the test and let you know exactly what's going on there. But it's the number of moles per liter. So exactly 1 liter, I'm a little fuzzy here. And unsaturated solution contains less than the maximum amount of solute. Unsaturated, less than maximum solute that can be dissolved. That is true. A saturated contains more than 100 grams of dissolved solid. Does that say anything about how much is dissolved in whatever? No. So this is false. Sorry, I'm going to take a drink. Too much talking. Okay, a solution can be made less concentrated by adding solvent. That's also true. Okay, here we've got a particular wine. Here's its concentration. What volume of ethanol is in this water? This amount of wine. Well, this is the percent on the test. That's the total of the test. So here's what I'm trying to find out is my test score. So here's my test score with everything there. That's the total on the test. I'm just reverse finding out what's going on. So I'm going to take x is equal to 15.2 times 1.5 and then divide it by 100. 15.2 times 1.5 divided by 100. 0.23 would, it's actually on the calculator 0.228, but 0.23 liters would be in of ethanol. Because volume to volume, I'm using the same volume, same kind unit. Sorry guys, I'm trying to make it through. A glucose solution is in an intravenous is this concentration. Here's the moles per gram. How many grams are contained in this? Well, right here it's weight per volume. So I don't need this. This is extra stuff. Ignore it. Okay, so here's my volume, which goes on the bottom, 1.50 liters. Remember I told you they're going to tell you, here's the percent right there, how to set it up. Weight is on the top, that's what I'm looking for, times 100 equals 5.2. So solving for x, x equals 5.2 times 1.5 divided by 100. 5.2 times 5.5 divided by 100, 0.078 is my grams of C6H12O6. Okay? All right, next up. Oh, I divided. Sorry, I thought that was awful small. Let's go back and fix that. And just times it. Yes, that's much better. 7.8 grams. Sorry about that. Okay, which solution contains the smallest number of moles of NaCl is what that's supposed to be. So basically, you are just going to figure this out. So weight per volume is usually grams per milliliter, right? You're going to end up with grams here. You're going to end up with moles here. And then it says the same. So instead of going all the way to moles, if you find out which one has the most grams, then you're going to be good. So the only one I have to do something with is this one. So we're going to take this times this. So 2,000 times 4.0 times 10 to the negative 5. And I get 0.08 grams. Here I'm going to take 20 times 4 times the 58.44. Okay. And I'm going to get 467.5.2 grams. And then this bottom one, I'm going to take 2,000 times 4, and I'm going to get 8,000 grams. Oh, but I forgot to do something here. And I forgot to do something here. So let me go back. Oops, this is my boo-boo. All right, remember that this is X divided by 200 milliliters times by 100, or 2,000, sorry, is equal to 4.0 times 10 to the negative fifth. So I'm not just doing that, I'm taking 4.0 times 10 to the negative fifth, timesing it by 2,000, whoops, I didn't bring it down, negative fifth, bring it down, and then I'm going to times it by 2,000, and then divide by 100. So I actually got 8 times 10 to the negative 4 here. On the bottom one here, this one is actually X divided by 2,000 times by 10 to the 6th equals 4. So to solve for X, I'm going to take 4 times 2,000 divided by 10 to the 6th, and I end up with 0.008. So the winner is, oops, let's make double sure here. Oh, it's milliliters, so I forgot to do this one right too. Boy, weird, I am betting 100 here. So I've got to change the 20 and divide it by 1,000, and that would be 20 divided by 1,000. I better do it in the calculator since I'm having issues right now. 0.02 liters. Now I'm going to times it by the 4, and I get 0.08. So it still is the most. All right, that was a hard one. Let's see if I can keep. This is what happens with Friday night after school. So how many grams are contained in this many milliliters of this? Change that right away to liters. 777 liters by dividing it by 1,000. We're going to take it and times it by 2.43 molar, because that we can get moles are equal to molar times liters. Okay, so if we do that, 0.777 times 2.43 gives me 1.888 moles. Then I just need to add this up. So C6 times 12.011, H 12 times 1.008, O 6 times 15.999. Adding that all up. Is 180.156, and I'm going to do 1 mole, 180.156 times 0.1888, and I get 340 grams, C6H12O6. There we go. Okay, the next one. Which solute has the greatest, sorry about the T, mass of solid? So these are the same, so it has to be with this. I'm looking for the greatest mass. This one you can do really fast. So calcium is about 40. So we have 40 plus nitrogen, we have 2 of them, so 2 times 14 plus 6 times 16, get an answer. This one would have 2 times 23 plus 12 plus 3 times 16, get an answer. This one is, we've already done, 58.44. This one would be, calcium is 40 plus 2 times 35. And we're going to get answers here, just real fast, dirty answers, not exact ones. So we've got 40 plus 28 plus 6 times 16, and we end up with 164. We got 2 times 23 plus 12 plus 3 times 16, and we get 106. And then this one is 2 times 35 plus 40, and we get 110. So you can see that one's going to have the greatest solid. So that's real quick. All right, gotta hurry. Running out of time. Okay, which of the following would be most soluble in water? You're looking for the smallest that has hydrogen bonding. Both of these are small that have hydrogen bonding, but this one has 2 sets of hydrogen bonding, so it would be this one. Okay, and this one is another C1V1 equals C2V2. Here they're giving you percent, volume, percent. So you have a concentration, you don't know the first volume, you have a second volume, and you have a second concentration. So you're looking for V1. So you're going to have C2V2 divided by C1, plugging in. 0.175 times 450 divided by 3.25. Quick and dirty, 0.175 times 450 divided by 3.25. 24.2 milliliters. Done. Okay, which has the lowest circle in blue, which has the highest circle in red. So I'll use pink. So I'll use blue, and then I'll use pink. All right, so here again, same. Same. So I'm looking for I here. It's all about I. How many parts will it break down in? This one, 4, 1. This one, 3. This one, 2. So the smallest, the lowest boiling point is going to be the one that has the highest I. So lowest boiling point has the highest I. The highest boiling point, and I forgot the T there again, sorry, has the lowest I. Okay, so this one right here would have the lowest, or the highest boiling point because it has the lowest I, and this one right here would have the lowest boiling point because it has more I. So the freezing point depression here would be greater than the freezing point depression here. Okay, what happens to cells when they are placed in isotonic solutions? Nothing. When they are placed in hypertonic, that means higher, that means that the cell is going to go to cremation because it's going to try and dilute the outside. Hypotonic means it's lower solution than the cell, and so the tries to get in and blows up the cell, which is lysed. The cell's been lysed. Okay, bottom one here. What is the molarity? Again, what is the molarity of this isopropyl alcohol solution? So we're looking for molarity. Molarity is moles per liter. We've got volume to volume. We know the density of isopropyl alcohol is this, and the molar mass is this, and the density is this. Okay, so this right here says that I've got, if it's 15%, that means originally, remember that I had something over, and we can choose a number for the bottom here. I'm going to choose 100 just because it's easier. Times 100 would equal 15%, right? Well, if it's 15%, this x is equal to 15. So if I choose 15, that means I have 15 milliliters for every 100 milliliters of water. Well, I want the top to get to moles, and I want the bottom to get to liters. So that's really easy to do for the bottom. There's 1,000 milliliters in 1 liter. Boom, boom, and we're in liters. So now I've got 15 milliliters over, well, I probably should, 150 milliliters over a liter. Now, once I've got to this point, this is where I'm going to use this to change it from milliliters to grams. So here I'm going to put 0.786 grams in a milliliter. The milliliters will cancel. I take that 150 times it by 0.786, and I've got 117.9 grams per liter. Now it's still not moles on the top. That's where this comes into play. So I put in the next one, 60.09 gram. Whoops, put it on the wrong place. That's what happens. 60.09 grams divided by mole. That mole will actually flip up to the top. And we'll take that 117, divide it by 60.09. And we now have, because grams will cancel, we now have 1.96 moles per liter, which is 1.96 molar. Okay, next one. The molarity of solution. What is the molarity if this? Here's this. All right, so we've got weight versus volume. So again, we can assume that we have 21.5 grams in 100 milliliters. Again, changing, because remember this is grams and milliliters. Changing this really quickly. I can change the milliliters to liters. Boom, boom. Now I've got grams per liter. That's where this comes into play. I put the mass down here because I want to get rid of it. And that actually flips the mole on the top. Grams go out. And I can put it all in my calculator in one. So you see in the other one I broke it down. This one I did it faster and dirtier. So 21.5 times 1,000 times, I just cleared the whole thing. 21.5 times 1,000, enter, divided by parentheses 100 times 180.16, close parentheses. We end up with 1.19 molar glucose. Done. Okay, the maximum level of copper drinking is this, milligrams per kilogram. What is the concentration in parts per million? So parts per million, we want these to both be the same, and we want to times it by a million. So we've got milligrams and kilograms. So let's start with 1.3 milligrams divided by kilograms. So I need to get them both in the same units. So I'm just going to get them to grams because it's easier. So I'm going to go milligrams. There's 1, like milli means 10 to the third milligrams in 1 gram. And then on kilograms, I'm going to go, there's 1 kilogram. So I want to get rid of kilograms. I want to go to grams. It's 10 to the third grams. Okay, so kilograms cancel, milligrams cancel, and I've got what I need. So 1.3 divided by parentheses 10 to the third times 10 to the third, those parentheses, and I get 1.3 times 10 to the 6, negative 6. Now, that is just the starting point. I need to get it in parts per million. That means I need to times it by 10 to the 6 because this is my fraction right here. This whole thing right here, that's my fraction. So I'm going to times it by 10 to the 6. When I do that, those two basically cancel themselves out, and I end up with 1.3 parts per million. Okay, next one here. An unknown amount of water is added to 25 milliliters. Here's volume 1 of this. That's concentration 1. What can be said about the concentration of the resulting reaction? Well, if I'm going to add water volume, then what's going to happen to concentration? Concentration is going to go down. So what can be said about the resulting concentration? It will be lower. Okay, next one. Magnesium hydroxide can be made by the reaction shown below if the chemist requires this much moles of NaOH for this reaction. What volume of this is needed to provide this amount? Do I need this equation? No. Extra information. I do have molarity equals moles divided by liters. I am looking for liters. So I am going to switch these two places, and I'm going to get liters is equal to moles divided by molarity, and I'm going to plug in 2.725 divided by 3.50, and I get 2.725 divided by 3.5 gives me 0.779 liters. Done. Next. Almost finished, guys. All right. What happens to the number of dissolved particles in a solution as the osmotic pressure increased? So, happens to the number of dissolved particles in a solution as the osmotic pressure increased. So, as I'm increasing osmotic pressure, as I'm pushing stuff through, the number of dissolved particles isn't changing. It's just trying to equalize and make an isotonic solution. That's the goal. It wants it to be the same on both sides. So the number of particles don't change. What things determine if a compound is soluble in water? You've got NOF, you've got NAGSAG, and those are the ones you want to really concentrate on. Okay. Next one here, we have the solubility of this in water is at this many grams. If I have that many grams per this of water, all of the NaOH will dissolve, and the solution results will be unsaturated. This question is a little bit hokey. So it's saying at 20 degrees, this much will dissolve in here. Well, if I have 160, then I should need 200 grams of water for it to dissolve. I only have 150. So because of that, it's not going to be unsaturated. If all of it dissolves, then I have had to heat the temperature up to make it a supersaturated solution. But if I haven't heated the temperature up, if I kept this the same, then it's just a saturated solution, and I have stuff that's not dissolving, solid down here at the bottom that's not dissolving. Okay? The only way I'm going to get all of this to dissolve in that is I'm going to need to raise the temperature to make it supersaturated. Okay, the last one right here, the concentration of weight per volume percent is this. They just want you to know it's grams and milliliters, and we're done. Have a great day. If you need help, Monday before school or Monday during tutorial. Test is Monday. Good luck.